Hi, my name is Stephen Wang. I'll be presenting workshop 2 for CSC 575 Algorithm and Complexity Analysis of fall 2021. So we'll get started with the original problem. Given a matrix M of integers and an integer value of v, is there a square matrix with an M whose values add up to v? Now, note that matrix M may be a rectangle. Integers may be of any integer, so positive, negatives, and zeros. We must be able to consider single cell or size 1 matrices with an M in addition to larger sizes up to the maximum allowable for that matrix. So that's defined by the X or Y, whichever is smaller. The professor did provide a brute force algorithm, and it must be improved upon using my algorithm, the time complexity. The space complexity may increase, but we cannot use additional processors or cannot parallelize the algorithm. Your new algorithm should have the same parameters, so that means it should take the matrix M and value V, and that's it. That's what the driver function has to be able to take in. So we'll go through a brief outline. We already introduced the problem. I'm going to run through my program and the solution. We're going to take a look at the time complexity, so the worst and the best. Then we're going to take a look at the space complexity, and then we're going to take a look at proof of correctness. So my original code here, as you can see, is follows the same format. I use the professor's brute force algorithm as a starting point. We have test as the only function, and test really here is for saying yes or no. The real driving function is going to be the check matrix here, which I've adapted. So instead of running through brute force, what I've done is I've created two sub matrices, and I'll explain the logic behind them now. If you'll notice, we have submatrix horizontal and submatrix vertical. What submatrix horizontal's goal here is, depending on the search parameter or the current size variable, we are going to create subtotals or subsums, right, based horizontally. So for example, for cell 1, it'll be cell 1 plus cell 2 because it's going to be a size of 2. So these two cells will add together and create this one. 2 and 3 will create the second cell, 3 and 4 will create the third cell, and then I have a few examples here to show where they would align. If you'll notice, because we are adding together horizontally, the x-axis will shrink, and it'll shrink dependent on the current size or the search size. For example, with the same 4x4, I've now created a 2x4. This will be 1, 2, 3, 2, 3, 4, 5, 6, 7, 6, 7, 8. You can see very clearly how this is a simple horizontal shift, and it creates a submatrix, right? Vertical is the same kind of logic, just in the other axis. For the first cell, it'd be 1 plus its direct bottom, so 1 and 5, 2 and 6, 3 and 7, 4 and 8, and this would be for a size 2 search. If you imagine a 2 square, this is the y-axis of that, searching 2. Unlike horizontal, as you can see from this graph, we are no longer shortening horizontally, but rather vertically. So a 4x4 has turned into a 4x2. 1, 5, 9, 2, 6, 10, 3, 7, 11, those become the first 3 cells. So this is the purpose of the functions, and the reason behind this is we're breaking the problem down into smaller parts, so that ideally we do this. We take our original matrix, your original 4x4, and then you push it together horizontally, you create 1 plus 2, 5 plus 6. And then with the same search size, then you add together 1 and 2 and 5 and 6. This one cell has now become the sum of these 4 cells, or the sum that we're trying to search for. And then so you can compare the values inside of this matrix with your search value V. And ideally, this will create more space complexity, but save on time. So let's take a look at our time complexity here. I'll start with submatrix horizontal. You can see here, it looks very complicated, it looks very daunting, but that's because I kept current size as a variable as more of a personal intrigue point. Note that when we commit to running function submatrix horizontal, current size is a known constant. This depends on which iteration is going through, but at the moment that you run this program, your current size is confirmed. It is a constant for all pretenses here inside this function, for all intents and purposes. So what ends up happening is this end result, if you want to consider curve size as a variable, but we don't, and you end up with a time complexity of x and y. This makes sense logically because ultimately you're taking the original function, you're taking the original matrix, and you're really just adding things together, which are C statements, a bunch of C statements, and then you're recreating an X and Y, a new matrix. So the number of iterations needed is dependent on the size, and you're just creating a new matrix, X and Y. It's the same for submatrix vertical. You end up with a very similar formula with current size, but ignoring it since it's a constant, once again, you're going to have X, Y. So here, the time complexity is going to be X, Y. Now, best case versus worst case, in my functions, they are the exact same thing, because no matter what, as long as you start with a viable matrix, you're going to end with a viable matrix. And the assumption is that we always start with a viable matrix. And so no matter what, you're going to run through the same process. There's no variation in this. So you're going to have the same time complexity no matter what, which is X and Y. Now in the driver function here, we'll start with the best case time complexity because it's a little bit simpler. It always is, right? In this, the only function that I didn't create myself is the min function as described in the prompt. I need to define it. So there's my reference here. It is a constant because it's a comparative between two variables. So it's going to have a value of C. We have one time because it's going to be the first iteration. So this is going to be 1. This is XY for the submatrix creation. And then this is going to be the check loop, which is going to be found on the first column and the first row. And then it's going to, well, first row and then the first column, because this is supposed to be Y, this is X. And then we have C plus XY plus C, or else just a time complexity of XY. That's going to be your best case scenario. Now, your worst case scenario, you're going to have to run through all of it. You're going to have to run through up to K, whatever K is, which is the minimum of X and Y. You still have XY and XY, you still have the C, and then you have Y minus current size plus 1 times X minus current size plus 1 times C. This is because the current size, where it's found between 1 and K, we don't know. It's by current size, whatever the solution size is. And then you have to search through it from X, Y, and then this statement C. So adding it all together, you end up having something really messy. You have something that looks like this. But you have to remember that K is a derivative of X and Y. It's just a minimum of X and Y. And C is also a derivative of K. It's just K minus however much, right? It's 1, 2, 3, 4, 5 up to K. So knowing this, you can simplify this down to KXY or XY times the minimum of X and Y. And this is because ultimately all of these are derivatives of X and Y. They're not truly random. They're not a truly unknown sense of numbers, so to speak. You could rewrite this as K minus N here, for N being whatever the difference between C and K is, or the current size and K, and you'd be able to have a very, very similar value in this regard. So since these are the largest values, I found that this is going to be the cleanest O that I could find. So XY times the minimum of X and Y. Now we go into the loop invariant proofs. Loop invariant horizontal, vertical, and the driver function is what I have, but they're all very, very similar because they all run through the same brute force algorithm logic. So these are all derivatives of the loop invariant that was provided to us in the previous practice problem. So for all cells in rows 0 through 1, right? Whatever the current search term ij, that is the sum of matrices ij up to ij plus the current size minus 1. And the idea of that is it's going to be the sum of all of those horizontal cells dependent on the current size. And then the second half here for cells within row I plus 1, the idea is that we check everything within I plus 1 and we continue to move forward. So this follows the same logic of brute force algorithm that we checked every single square to create our new submatrix as sums. So we begin with a completely empty submatrix 0, 0, 0, and this is true as no values have been processed yet. And then through maintenance, we assume the loop invariant has been maintained up to row I plus 1 and column J plus 1, and then there are 3 possible cases, right? So once you've hit the very last cell, since we go left to right, once it breaks through that first loop, and if there are rows still remaining, then it continues on to the next row, column 0, and then you sum according to the rules of the loop invariant. We can see that in my matrix, in my formula here, right? right here in horizontal, what this is going to do is this is going to run through all possible, I believe this is rows, and then this is going to be columns. Yep, this is going to go left to right and then up and down. And then this is going to search for all the relevant sum squares. So once this breaks out of this loop, it'll go to the next iteration of this top loop. If there are no more rows remaining, then the loop ends, and then we can see the termination case. And if it's below, then it just goes to the next point, right? So in terms of termination for loop invariant horizontal, you only terminate when there are no more columns and rows left in my matrix to search through, and it'll return a brand new submatrix 1. So this kind of lends credit to the idea that we are creating a new submatrix 1 that should be the sum of horizontals depending on the current size search. And that's the point of the function. Vertical is similar, it's just different axes, it's different dimensions, right? All of these are very similar for all cells within row 0 through I. You maintain the same column, but then you start adding upwards. So yeah, like you follow the same logic here. You go through all cells within row I+1. So this is saying that for the next cell, this is what you would do. This is what the sum would be. And then initialization begins with the completely empty matrix, sum matrix 2, 0, 0, 0. And this is true as no values have been processed yet. Same idea. It's different because, like we mentioned before, the dimensions shrink differently depending on the type of sum that you're trying to do. With vertical, we don't have it dependent on current size. It's x-1 instead. And then the termination result, it's only due to having no more rows left to search within my matrix, and you return a new submatrix 2. So this should be another submatrix, it's just summed vertically instead, right? And we can see this in my code here with vertical. So we run through y minus current size, that's going to be the number of rows, and we maintain the same number of columns. It doesn't shrink horizontally, it shrinks vertically. And then as you can see here, we have a sum plus equal for dependent on mj instead of ij, so it's going to be below, and is going to just sum up into I and j, its original root search, or the origin point, right? And we have the same thing here for horizontal. This is how we know that it works the way that it does. It runs through in this loop all of the relevant squares in the search parameter. Now, what does this mean for our driver function? Well, for all sizes or search sizes between 1 and k, you end up with submatrix 2, I and j, is the sum of all values between I and j in my matrix, and then I plus cur size minus 1 and j plus cur size minus 1. The idea is that's trying to describe mathematically that for this search term and for a specified cur size, we're going to reach out and sum all this together. And it follows using this logic that I presented here. So assuming that the loop invariant has been maintained, well, initialization begins with a completely zero matrix, and sum 0, 0 is 0 at initialization, as this is true as no values have been processed yet. So we assume that the loop invariant has been maintained up until this point, and then we have C, as long as C is less than K, and then J plus I, it hasn't broken past, well, it has broken past the rightmost square in a row, then it'll advance on to the next row. If there are no more rows remaining, then the loop searches for C plus 1 cur size. And if C is greater than K, then that's a termination case for the entire function. And then if J plus 1 is less than or equal to X minus 1, this is meant to be submatrix 2.size. In this case, sum the values according to the loop invariant at origin I plus 1, J plus 1. And in termination cases, you have two cases. It either returns true because after it searches through all of submatrix 2 and it finds value equal to V with a search size of C, then it returns true. This is because we searched through submatrix 2, and as described before, we know that to be the sum of all relevant squares for that search term. Return false, no value within submatrix 2 by any search size defined by search size C less than or equal to K contains a value equal to V. And that means that we searched through the entire thing brute force and we didn't find anything. Now, I know I left a part out for initialization, and that's because I wanted to run through this very quickly to kind of show that that is how it works. So at 0, 0, at the very beginning, right, we start at 0, 0, we start at 0, 0 for a size, let's say a search size of 2. It'll go from 0 then to 1, but it can't go past that because it's j plus 2. Right, is going to be 0, 1, and then that's it. And so that means for I and j, it's going to be the sum of 0, 0, 0, 1, and it's going to create that horizontal. And then that's going to complete the first iteration. That is exactly what happens in the horizontal. And this will change depending on cur size. For vertical as well, you start from 0, 0, it's going to be y minus 0. You're going to end up 0, 0 for search term of y minus 2. That's how many columns can go through, right? From 0 to y minus 2, x minus 1 here, you're going to start adding up based on the cur size, but instead of changing from the x value here, or where it is on the column, you're going to start changing it on where it is, where it is on the row, you're going to start changing it on the column for vertical. And that's the initialization for that point. And then for the driver, as long as C is in between 1 and K, which it is, right? And then we run through these programs to add together. Then following the logic, as we know, as we've seen, as I described here for 0, 0, and I've shown directly, right? As the initialization, it'll search through that term and it'll search through for V, because it'll start at 0, 0 in submatrix 2, which would be, in this case, just in this example case, it would be this. So those should be the initialization proofs. Thank you very much for listening to my presentation. Hopefully I was clear, correct, and I was able to explain myself properly. I hope you guys have a great night. Thank you very much.